12 lines of LangChain. Worked in the playground. Shipped to production. 3 weeks later, it cited a contract clause that did not exist. Nobody could debug it. Chunking, embedding, retrieval, generation, all buried behind 4 layers of abstraction. You cannot fix what you cannot see. Today, you and I build retrieval-augmented generation from scratch. No LangChain, no llama index, no vector database, Python and embedding endpoint, and NumPy. Every layer visible. There is one failure mode that kills accuracy silently. Every framework hides it. Most tutorials skip it. We will get there. 5 steps. Chunk your documents. Embed them. Store the vectors. Retrieve what matters. Generate with grounding. Starting with the step most teams get wrong. 2020. Patrick Lewis at Facebook AI Research published Retrieval-Augmented Generation for Knowledge-Intensive Tasks. 32 pages that changed how we build with language models. The idea is embarrassingly simple. Instead of hoping the model memorized your answer during training, fetch the relevant documents first and paste them into the prompt. External memory on demand. Context windows grew from 4,000 tokens to 1 million. Should be dead. It is not. Stuffing 1 million tokens into every call costs real money. Retrieval lets you fetch the 5 paragraphs that matter. There is a step between retrieval and generation that most tutorials leave out. It is the difference between a system that works and one that hallucinates confidently. Hold that. Step 1. Chunking. You have a 100-page document. You cannot embed the whole thing. You split it into pieces. How you split determines whether your system works or hallucinates. Naive approach. Split every 500 tokens. 4 lines of Python. This works for demos. In production, it cuts sentences in half and retrieval falls apart. The fix is recursive splitting. Try paragraph boundaries first. Too big? Fall back to sentences. Then words. You preserve semantic units instead of cutting blindly. Overlap your chunks by 50 to 100 tokens. If an answer spans 2 chunks, the overlap captures it in at least 1. Without overlap, you lose information at every boundary. Chunk size. 256 tokens for precise retrieval. 512 for broader context. I use 384 with 75 token overlap on most production systems. Start there. Measure. Step 2. Embeddings. Turn text into a vector. A list of floats. Similar meanings land near each other in vector space. No magic. Here is the raw call. No framework. Post to the embeddings endpoint with your text and model name. Back comes an array of 1536 floats. That array is your chunk's identity. To find similar chunks, compute cosine similarity. Dot. Product divided by the product of magnitudes. In NumPy, that is 1 line. Score of 1 means identical. 0 means unrelated. Which model? Text embedding 3 small. 2 cents per million tokens. 1536 dimensions. Handles 95% of use cases. Do not overthink this. Batch your chunks. Do not send 1 call per chunk, up to 2,000 per request. Same cost, 10 times faster. Step 3. Storage. Everyone says you need Pinecone or Weaviate or Chroma. You do not. Under 100,000 documents, NumPy in memory is faster than any managed vector database. Stack your embeddings into a NumPy matrix. To search, compute cosine similarity against every row and return the top k indices. 8 lines of Python. That is your retriever. For persistence, save as a numpy.npz file or use SQLite with a blob column. Both survive restarts. Both are zero dependency. Production does not require a managed service at this scale. When do you need Pinecone? Over 500,000 documents, multi-tenant filtering, real-time updates from multiple writers. If none apply, skip the vendor lock-in. I have seen this pattern 3 times this year. Team picks Pinecone before they have 1,000 documents. Infrabill hits $400 a month to search a corpus that fits in 12 megabytes of memory. NumPy would have been free. Step 4. Retrieval, not keyword search. You embed the question with the same model and find the closest chunks, semantic meaning, not string matching. Embed the question. Search with k equals 20. You get 20 candidate chunks ranked by cosine similarity. Not all 20 are relevant. That is the problem. Remember that missing step? Reranking. Your embedding search is fast but approximate. A re-ranker uses a cross-encoder that reads the question and each chunk together. Much more accurate. Jina and Cohere both offer re-rank endpoints, one call. Send your 20 candidates, get back 5 with precise relevance scores. Your top 5 go from roughly relevant to exactly relevant. Semantic search has a blind spot though. It catches meaning but misses exact identifiers. Function names, error codes, version numbers. You need keyword search alongside it. Production systems run semantic and keyword search in parallel, then merge with reciprocal rank fusion. Aman Sanger at Cursor built their code-based search this way. Together they cover each other's blind spots. Doe Kiela, co-author of the original paper who now leads contextual AI, said it directly. The quality of your generation is bounded by the quality of your retrieval. A perfect model with bad retrieval is still a bad system. Step 5. Generation. Inject your re-ranked chunks into the system prompt. The pattern. Here are the relevant documents. Answer using only the information provided. If the answer is not in the documents, say so. Nelson Liu at Stanford proved something critical in 2023. Models pay the most attention to the beginning and end of the context. The middle gets lost. Put your best chunk first, second best last, everything else between. Add one instruction. For every claim, cite the source by number. If you cannot cite a source, do not make the claim. This single rule cuts hallucinations by roughly 60%. The model becomes a reporter, not an oracle. The full generate function. Build context from chunks. Format the system prompt. Call the model. Stream the response. 15 lines. No framework needed. You now have a working system in under 200 lines. Chunk, embed, store, retrieve, re-rank, generate. You understand every layer. Now let me show you where it breaks. Remember that silent failure? Embedding drift. You embed documents today. 6 months later, the provider releases a new model. You embed new documents with it. Old and new vectors live in different spaces. Similarity between them is meaningless. The fix. Version your embedding model. Store the model name alongside every vector. When you upgrade, re-embed everything. 100,000 chunks costs about $2 to re-embed. Cheap insurance. Failure 2. The answer spans 2 chunks. Your retriever finds chunk 7 but misses chunk 8. The model presents a partial answer as complete. You never know you missed half the information. This is why overlap matters. Failure 3. The retriever returns chunks that are topically related but factually irrelevant. The model answers anyway because you told it to use the context. Confident, cited, wrong. Re-ranking is your defense. You have no idea if your system is improving unless you build an evaluation set. 50 question-answer pairs. Run them after every change. If you skip this, you are flying blind. Cache your embeddings. Same question comes in twice, skip the embedding call. A dictionary with the question hash as the key saves real money at scale. Attach metadata to every chunk. Source file. Date. Category. Filter before you search. User asks about the 2026 policy. Exclude chunks from 2024. Smaller search space. Better results. Here is your complete architecture. Document in. Chunker splits it. Embedder vectorizes. Store persists. At query time, embed. Filter by metadata. Retrieve top 20. Re-rank to 5. Order by the lost in the middle rule. generate with citations. I am not saying never use LangChain. I am saying understand what it does first. Once you have built this, you know where the framework helps and where it hides your bugs. That is the difference between using a tool and depending on one. 80% of retrieval-augmented generation quality comes from two things: how you chunk and how you re-rank. Not the model, not the database. The parts most teams spend the least time on. Next time we take this system and add agentic capabilities. A retrieval system that decides when to search, what to search, and whether the answer is good enough. That is agentic retrieval-augmented generation. If this saved you time, subscribe. We do the deep dives here. Architecture, not tutorials. Hidden edge case I missed? Drop it in the comments. See you in the next one.